Hi friends, welcome to my channel NM Learn My Courses with Nagmani. Today we are going to see types of loads on beams, and in previous class we discussed types of supports and types of beams. Okay, if you see the types of support, there are four types of supports. One is simple support, roller support, third one is hinged or pin support, fourth one is fixed support. And similarly we classified about types of beams. We discussed about types of beams. Here one is statically determined beams, another one is statically indeterminate beams. And if we see here, in statically determined beams classified into four types. One is simply supported beam, and one is beam with one end hinged and another end is roller. And next one is overhanging beam. Last one is cantilever beam. And in if we see statically indeterminate beams, here also is it classified into four types. One is continuous beam, fixed beams, and propped cantilever beam, and beam with both ends hinged. These are the types. Who did not watch this class, please first watch this class and next continue with today's class. Okay, that is types of loads on beams. This is also there are four types of loads on beams. One is point load, another one is point moment or couple moment, third one is uniformly distributed load, fourth one is uniformly varying load. And if we see the point load can also be called as concentrated load. That means if the load is acting at one particular point, then it is said to be point load. If we see here, we can define this force as F1 load and this is F2 load. These two loads acting on this beam. So this is called as point load. These point loads also acting on some area. So this area is very small compared to the big volume. So it can be treated as point load and it can be indicated as at one particular point. This point load can be indicated at one point. Okay, and if you see the next one, point moment or couple moment, that means if the moment is acting at one particular point, then this called couple moment. We will see how to solve this type of problems while solving the problems. Okay, and next one is uniformly distributed load. In the name itself, it's saying that the load is uniformly distributed. Okay, the load is uniformly distributed. And next one is uniformly varying load. This uniformly distributed load can be called as UDL. Okay, uniformly distributed load. And the next one is uniformly varying load. This is also called as UVL. Okay, uniformly varying load, and it is subcategorized into two types. One is triangularly distributed load, next one is trapezoidally distributed load. Here the load is distributed in a right angle triangle manner. If you observe this is his right angle triangle. The load is distributed in this way. Then this type of loads are called triangular distributed load. And here if we see here, this is the trapezoidal shape now. So this is called a trapezoidally distributed load. So these are the types of loads on beams. And for solving problems, we have to convert this uniformly distributed load and uniformly varying load into point load. Then only we can solve the problems. So how to convert this uniformly distributed load and uniformly varying load into point load, I will explain here, and please listen carefully. Okay, and here this load is uniformly acted over a length. Okay, in this length this load is uniformly distributed. So this can be converted as, this one is I am writing. So here if you same I am writing the beam here. So here these are the reaction forces at the end, RA and RB at point A at point B. Okay, and if you see this one as length L, okay, this one as length L, then this uh, uniformly distributed load can be represented as omega. So this omega can be acted at the center of this length, okay, whatever the length which is distributed in half of length, that means here L by 2 and here L by 2, okay, here L by 2. Here the load is again omega into L. This is formula kilonewtons. This is Newton per meter. Okay, sorry, kilonewton per meter. Okay, I will explain same this one with the another example. Okay, here the load is distributed in small length. Small, if it is a capital L, then in small length the load is acting. So this uniformly distributed load can be converted into point load when this omega, this is the load omega into L, then this is load F1 is equal to omega into L. This is not load which is acting at center of this given length, this distribute. So if you see here, this is acting total length L. So this can be represented as, and in some problems I am representing here beam with I am representing here same beam, and this uniformly distributed can also represented as like this. Okay, in problem they may give in this way, like this one is omega, or in this way. Okay, whatever it may be, don't confuse. And if it is acting at a whole length, then this can also be if we want to convert this load into point load, then we can convert. See, if you see here at point, at the same midpoint itself, the load will be acted omega into here capital L. This is L by 2, capital L by 2, here also L by 2. In this way we can convert this uniformly distributed load into point load. So if it is uniformly distributed load, then the load will be act at the center of that given span of the length, and that load which is equal to omega into L. Okay, this is you have to remember while solving the problems. And the next one is uniformly varying loads. Okay, and now if you see this is triangularly distributed load. If you want to convert this load into point load, then see here, if you want to convert this triangularly distributed load into point load, we have to convert. If you take this beam, this the length of the beam is L. So if we want to convert this if we want to convert this triangular distributed load into point load, then we have to, this is they are given load as omega. So if the load will act at the L by 3 from the base, like this maximum, from maximum point from the base to L by 3, the load will be acted, which load is omega into same length. So here the units for this load is kilonewton per meter. This is Newton per meter or kilonewton per meter. So we are multiplying with L. So here we will get kilonewtons. So this is the load which is acting at L by 3. This is L by 3 means this side is 2L by 3. Okay, understood? In this way we can convert triangularly distributed load into point load. If we see a trapezoidally distributed load, here same as this only. Here if you see here if we off this section, like if you house, this is nothing but uniformly distributed load, and if we see above this line, this is triangularly distributed load. So if you want, so this load can be converted into, okay, here This is I am writing same RA and RB. If it is at a length L, then yet if we see this uniformly distributed load here, okay, here this is omega A and here omega B. The load is varying na, so here omega A load will be acting, here omega B load is acting. So if you see here, this is nothing but uniformly distributed load. How much load is acting uniformly distributed? Omega B. So uniformly distributed load will be concentrated at the center of this load. If you want to convert uniformly distributed load, so at the center at L by 2, the uniformly distributed load will be acting. So omega B into this L. And if you want to convert, if we here we have trapezoidal, this triangularly distributed load. This load will be concentrated at the L by 3 from the base. Okay, from L by 3 from the base. This is nothing but, and how much load is acting here? Omega A is this total load is acting on the beam. So here only we need this much height. What is that? Omega A minus omega B is nothing but that load, omega A minus omega B into L. Okay, understood? In this way we have to solve this problem. Okay, if you want to see once, I will explain again. So if they give trapezoidally distributed load, here there are two types of loads are there. One is uniformly distributed load. If we consider only this part below this line, this is uniformly distributed line. If we consider above this line, uniformly like a triangular distributed load. So uniformly distributed load, if we want to convert this uniformly distributed load into point load, this load will act at the center of this length. So at L by 2, the load is acting. How much load is acting here? Omega B times of load is there. So this omega B into L times of load is acting at L by 2. And if you see this triangular distributed load, the load will concentrated at L by 3 from the base. Base means this maximum side, right angle side. So L by 3 from base. How much load is acting here? This is the total load acting on the beam. So we need only this much of height. Already with this much of load is indicated here. So we need only remaining height. So that is omega A minus omega B. And up to here, so L, so into L. In this way we can convert this uniformly distributed loads into point load or uniformly varying loads into point load. Okay, here one more thing, in uniformly distributed load, this load is converted into point load by multiplying with this length into this given omega. So in uniformly distributed load, for converting this into, we have to multiply this with 1 by 2 into omega into this L. So I forgot to mention 1 by 2 in the before explanation. Please make sure that here we have to multiply this 1 by 2 into omega into L. And similarly for trapezoidally distributed load, the everything is same, but we have to multiply with 1 by 2 in this. It indicates that here if you see this one, this is nothing but rectangularly distributed load. It seems like rectangularly distributed load. So if for a rectangular area is omega into L something, if you take this rectangular A B, so if the area of this rectangular is A into B, so in this way the omega into L, that load is acting at the center of given load. Okay, and similarly for a right angle triangular load, if we take this A and this one as B, then the area is half into AB. So in this way we have to write half into omega into L. And similarly for trapezoidally distributed load, here same for the triangular half into this area omega A minus omega B is nothing but height. This length is nothing but base. In this way we have to convert for right angle triangle. For the uniformly distributed load, for uniformly distributed load, that is omega B into L itself. Okay, in this way we have to convert the uniformly distributed load or uniformly varying load into point load. I will explain one problem so that each minute of this concept will be clear to you. Please carefully observe that problem so that you can understand and you can solve the problems easily. Okay, so this is the problem. This problem is beam. Here they are given beam A and B. I represented beam like this with line. I represented A, B. So here the beam AB, which having length this much, and it having point load and uniformly distributed loads and uniformly varying loads. This is trapezoidally distributed load. This one is triangularly distributed load. And now we will see how to convert these loads into point loads. Okay, and here they are given 5 newtons. So this is the point load, so no need to convert. So in the below, same I draw the with the same dimensions, I draw the this beam. Now these 5 kilonewtons will act at this point. So this is 5 newton. And yet this 3 meter span, the uniformly distributed load is acting. So the load which acts at the center of this given beam. So center for 3 meter is 1.5 meter. So at this center 1.5 meter from this side, this is also 1.5 meter. At the midpoint the load will act. The load is 8 into 3, that is 24 newtons. So this much of load is acting here. And similarly this is also uniformly distributed load, this is also uniformly distributed load. If they give in exam in this way or in this way, so no need to worry, both are equal. So for the remembering purpose only, I gave the two representation in one problem. Okay, so here they are given in this 3 meter span, the load is uniformly distributed. So the load is 5 newton per meter. So this load will act at the center. So center means for 3 meter 1.5, 3 by 2, that is 1.5. So 1.5, 1.5. At 1.5 the load is acting. What is the load? 5 into 3, that is 15 newtons. So 15 newtons load is acting. So here this is uniformly varying load, which is nothing but trapezoidally distributed load. And if you convert this into, if you write a section here, from here to this lower part is nothing but uniformly distributed load, which having 3 newton per meter. So this uniformly distributed load will act at this center. So for 6 meter the center would be 3 meter. No, so 6 by 2 is nothing but 3. So if we say this is 3 meter, this is also 3 meter. At the center the load will be acted, which is 3 meter. So 6 into 3, this is the 6 into 3, 18 newtons of weight is load is acting at the center of this 6 meter span. And here from here to here, this is nothing but triangularly distributed load. So here this is whole is 5. So we need this much of height. So this is nothing but 5 minus 3. So the load is will act from the base. From the base means from this height, from the base to L by 3. So L is 6. 6 by 3 is nothing but 3 to the 6. So 2. From here to here, this is nothing but 2 meter. This is 1 meter. Okay. From L by 3, the load will act. What is the load? Of into this height. 5 minus 3 is nothing but 2 into L is nothing but 6. So 2 will get cancelled here. 6 newtons of weight is acting at this point. Okay, understood? So once again, if you want to see, here this is the trapezoidally distributed load. So if you write a section here, the below section is uniformly distributed load. So if you multiply this 3 into 6, we will get 18 kilometer 18 newtons of this weight will act at the center of this 6 meter span. So center is 3 meters. So at 3 meters the 18 newtons is acting. So we are representing here. And this one is right angle triangle. So triangularly distributed load will act at the this load will act from the base. So from the base means here this is right angle. So from here to L by 3. L is nothing but here 6. 6 by 3 is 2. At 2 meter distance the load is acting. The load is off into this height into length. Height is nothing but 5 minus 3 is 2. 2 into this length 6. So total is this 2 get cancelled and 6 newtons. So that 6 newtons of load is acting at 2 meters. Okay. And now this is also, this one is uniformly varying load, which is right angle triangle. This side is right angle. So from this end to this side, this end to the L by 3, at L by 3 distance. So 3 by 3 is nothing but 1. So if we take from here to this side is 1 meter, at this point the load will act. What is the load? Off into, what is the height of this one? 5 into this base 3. So 15 by 2, 7.5 newtons of weight is acting at 1 meter from this end. So the remaining side is 2 meter. So in this way we can convert the uniformly distributed load or uniformly varying load into point loads. This will help you to while solving the problems, you have to create a free body diagram for the given problem. So for a free body diagram you have to convert every load into point load, then only you can able to find the unknown forces. So for that purpose you need practice on this type of example. So I think the concept is clear to everyone. For the reference purpose, I am going to add the screenshot of previous class and today's class. So if anyone wants, take the screenshot. And thank you for watching everyone, and keep support my channel, and please like, share and subscribe to my channel. Thank you everyone. Thank you so much for your love and support towards my channel.